Okay, so announcements to start with. This video starts on page 22 of the course notes or the blue book. During the course of the video, you'll pause it to do in-class exercise 4, which is on page 5 of the orange book. And then when you've done watch the whole video, there's a new standard deviation web assign that will be due Thursday, September 17. And I want to just make a couple little notes about WebAssign. I mentioned this earlier in the video now about logging into WebAssign, and this I think will make more sense to you now that you've actually had a chance to get in there and see how it works. So just everyone has different numbers on the numeric problems. So while everybody will have the same words, everyone has different numbers, and that means different answers. And then all these problems I've actually written all these problems myself, and behind every problem there's a little program that grades it. Okay, so sometimes, especially if I have a new problem that I'm just using for the first time that I've just written, there'll be a bug, and whoever reports the bug first gets a bonus point. So that's a incentive to do your homework early, because once someone finds the bug, I can go in and fix it so it doesn't stay that way for everyone. Now, a bug does not include like a typo that doesn't actually change the answer. So only if a typo actually changes the answer is it considered a bug. So also considered a bug is if an assignment pops up and it's not supposed to be there, if you're the first one to report that to me, or if, for example, this has happened several times before in past semesters, if I put something is due at 11:59 a.m., I'm never going to have anything due at 11:59 a.m. So if it ever says that, it's not because I changed the rules at the last second and didn't tell you. It's because I made a typo when I typed in the time. So please let me know that. Whoever tells me first will get a bonus point. Let's start by looking at these 3 small data sets. What's the same about these data sets? And what is different? Since they're already in order, we can tell that the center number on each one is 200. So 200 is the median for each of these 3 little data sets. All 3 are symmetric around the center. So 200 is also the mean for all 3 data sets. So what is different? Well, this one ranges from 100 to 300. This one ranges from 180 to 220, much smaller range. And this one ranges from only 198 to 202. So what's different is how spread out the numbers are. The first little data set has a range of 200, so coming from 300 minus 100 is 200. The second one has a range of 40 from 220 minus 180, and the third one has a range of 4 from 202 minus 198. And the fancy word for spread is dispersion. Now there's 3 ways to measure dispersion. One is the range, which is the simplest, and that's what we did up here. And really, this little example is the only time that we really will use the range much. Another one is the interquartile range, which we're not going to cover in this class. And the third one is the standard deviation. So as we talked about in the previous video, the mean is the balancing point of a distribution, and the standard deviation takes the approach of measuring the dispersion by asking the question, how far away are the observations from that balancing point. So balancing point is the anchor. How far away are the observations from that anchor? But before we talk in more detail about standard deviation, there's a couple definitions we need to get out of the way. And that's population versus a sample. And we're going to talk about this in a lot more detail. But for today, we need to know that the population is the entire group that we want information about. And the sample is just a part of that group. It's some subset of the population that we actually have data on. So for an example, let's suppose that we have 5 basketball players and their height in inches is 72 inches, 73, 76, 76, and 78 inches. So how do we find the standard deviation of our small data set of 5 basketball players? The first step is to find the mean. Okay, and so to find the mean, we're going to add up those 5 observations and divide by 5, and that gives us a mean of 75. The second step is to ask how far away are the observations away from the mean. Okay, and so to look at that, we have this table set up down here. Here's our 5 basketball players, and we want to calculate what we call the deviations from the mean, and that's the observation minus the mean. So the first deviation is 72 minus 75, the mean, gives us a negative 3. The next one, 73 minus 75, gives us negative 2. 76 minus 75 gives us positive 1, and so on. So next, we want to collect all these deviations into a single measure. And we want minus 3 to count the same as positive 3. So remember, the standard deviation is a measure of how far away the observations are from the mean. And both minus 3 and positive 3 indicate that the observation is 3 units away from the mean, just in 2 different directions. And one way to make negative 3 count the same as a positive 3 would be to take the absolute value. But there's a second way that we could make a negative 3 and a positive 3 count the same, and that is to square them. So why would we want to square them instead of just taking the absolute value, which seems like it would be easier? And so for those who have had calculus, the reason is that it's simple to take the derivative of a square, and it is impossible to take the derivative of an absolute value. And that is used in the derivation of the formula. So for those who haven't had calculus, or even for those who have, all you really need to know is that there is a reason it's not completely arbitrary, but it's beyond the scope of this course. So minus 3 squared is 9, minus 2 squared is 4, 1 squared is 1, and so on. And the next step is to add the 5 squared deviations to get the total squared deviations. And then to get the mean of the squared deviations, we can divide this 24 by 5. If we keep track of our units, like our science teachers always tell us to, here we have inches. Here we still have inches. But what do we have here? We have inches squared, which is a measure of area, not height. We want something that is in the same units as our original data. So to get back to inches, what we're going to do is take the square root of that 24 divided by 5 calculation. This symbol here is sigma. It's a Greek letter, and it's actually the Greek lowercase s. And that is our symbol for the population standard deviation. So that's one of our words from the previous page that we defined. And so sigma, the population standard deviation, is the square root of 24 divided by 5, which gives us 2.19. To get the sample standard deviation, there's the other word from the previous page. Our symbol for that is just S, our regular letter S. And here, instead of dividing by 5, we're going to divide by 4, which is n minus 1, or 5 minus 1 is 4. When we do those calculations, we get a final answer of 2.45, a larger number than we had for the population standard deviation. The population standard deviation is only appropriate if you have all of the data from your entire population. So for example, if I give you a test, you're my entire population. I don't care about the other students at UMF. I only care about my students. And so when I have your test scores, I have all the data from the population I'm interested in. So if I wanted the standard deviation, I could use the population standard deviation. Okay. But we almost never have all the data from a population. And in this class, we're going to be looking at data that comes from a sample or some subset of the population. And so for us, the sample standard deviation is going to be the one that we want to use. So why do we divide by n minus 1 instead of n when calculating a sample standard deviation? But before we get to that, first a thought question. What's the height of the tallest student you know at UMF? And what is the height of the shortest student you know at UMF? I have an advisee who is 6'8", and a couple semesters ago I had a student who was 4'10". So since I can't hear you very well, let's just go with that. So if our population is all UMF students, our population range is 80 minus 58, or 22 inches. And if you think your eyes are playing tricks on you, they're not. I did just correct that 70 that was there to 86. 8 is 80 inches. Now, let's suppose our class is a sample from this population. What's the height of the tallest student, and what's the height of the shortest student? And if I would have been thinking ahead, I could have asked you this on the student information form, but I didn't, so I'm going to just have to kind of make this part up. So let's suppose the tallest student is 6'3", which is 75 inches, and I am 5'2", so I'll use myself. I'm often the shortest one in the class, and 5'2" is 62 inches, which gives us a sample range of 75 minus 62 equals 13. So can the sample range ever be larger than the population range? What would have to happen for them to be equal? To be equal, both the tallest and shortest student, just by chance, out of the 2,000 students at UMF, both the tallest and the shortest would have to be in this class. And it's impossible for the sample range to be larger than the population range, because you can't have somebody that's taller than the tallest person in the population, or shorter than the shortest person in the population. So if we could go back to the previous slide for just a moment. So now notice what happened when we divided by 4 here instead of 5. Dividing by a smaller number gives us a larger result. Therefore, like the 2.45, the sample SD calculation is larger than the population SD calculation. So basically what we're doing is saying, well, we have this sample, and we know if we do the calculation for the population standard deviation, that result's going to be a little too small because we know our sample range is smaller than our population range. So if we know it's too small, why don't we just tweak it and make it a little bit bigger? And that's what that dividing by n minus 1 instead of n makes the sample standard deviation just a little bit bigger, so it's that little tweak we need to make it a better estimate of what the true population standard deviation is, which is a number that we don't know in our typical sampling situation. So that is a very intuitive explanation. So let's look at a slightly more theoretical explanation. So if we go back to that previous example and we look again at those deviations from the mean, if we add up those 5 numbers, what total do we get? -3 plus -2 is -5, plus 1, -4, plus 1, -3, plus 3 is 0. And this isn't just a coincidence. This will always be the case. Deviations from the mean will always sum to 0 because the mean is the balancing point. So in this histogram, you can kind of visually see how this works. The -3 and the +3, those are balancing each other out. And then the -2 is being balanced by the 2 positive ones. And since we know that the deviations are going to add up to 0, so if we only knew 4 of them, we could figure this last one out. So for example, these first 4 total up to -3, which tells us the last one must be +3. Thus we say only n minus 1 are free to vary, meaning once we know n minus 1 of them, we can determine the last one. It's no longer free to vary. So if we start with n pieces of information, we can summarize that information, but we cannot create more information. If we start with 5 basketball players, we can't create a 6th basketball player just using our calculators. So when we use our calculators to find this mean, it doesn't create new information. What it does is it sucks one of the pieces of information out from the original n pieces of information that we had. And since we need the mean to calculate the standard deviation, that means the degrees of freedom for the sample standard deviation are n minus 1. So your calculators will do standard deviations, but every model of calculator has its own subtle nuances about how it does standard deviations, and they're all just slightly different. So the easiest thing really is to just use a standard deviation calculator online. They're much easier to use actually than what you could do on your calculator. I have one here that's easycalculation.com, and the easiest way really to get there is to Google standard deviation calculator. So this used to be the top one that would pop up when you Googled standard deviation calculator. I just checked it myself now, and it's like down to number 8. And so there's many calculators online, and they all work pretty much the same. You should be able to use any of them. But if you want to use this exact one, you could either Google standard deviation calculator easycalculation.com all in one line, or go to easycalculation.com and then click on standard deviation calculator. You might have to look around on the screen a little bit because there's a whole bunch of calculators at this site. So to use this one, you enter all the numbers separated by a comma. So here's our example. And then you just click calculate. It gives you the total number of numbers you started with, the mean, and then it says standard deviation, and you don't need to worry about the variance. And then it says population standard deviation. So the one that just says standard deviation is the sample standard deviation. And if you're at a different calculator online, you can always double check and make sure that you have the right standard deviation by looking at both of them and remembering that the sample standard deviation is always the larger one. So if you have any question as to which one is which, sample SD is the larger one. And in terms of our symbols, sample SD is S and the population SD is the sigma. And on pages 27 and 28, there are 2 examples that say read on your own. These are larger, more involved examples, and I'm not going to go through them in a lot of detail, so I want you to do that on your own. But I'll just point out the highlights of the point that I'm making here in these 2 examples. And in this first example, here we have a population of 100. And in that population, the smallest value is 9, the largest value is 29. And here's the mean and the true population standard deviation, 3.12. Now, suppose you take a sample of 10. Now, the smallest value is 14 and the largest value is 22. So just like what we talked about, the sample range is smaller than the population range. And so that is the key point from this example. So it's important to understand how a standard deviation is calculated, but there's a reason why we want to use a calculator to actually do the calculations. First of all, it's really tedious and time consuming to calculate out a standard deviation the long way. But besides that, it's not very accurate to do it out the long way. Because in that example we looked at, the mean came out to a whole number, so the deviations came out to a whole number, and everything worked out beautifully, but that was a made-up example. In real life, the mean almost never comes out to a whole number. So you're going to round to some decimal places when you calculate the mean. So there's some rounding error in that calculation for the mean. And then you're going to find the deviations from the mean. And so every deviation also has that same rounding error in it that you had in the mean. And then you're going to take those that all have a rounding error in them and square them, making those rounding errors even bigger. And then you're going to add those all up. Now these are all really tiny little rounding errors that we're talking about. But when we square them and add them all up, it can throw off your answer just enough. So for example, it would get marked incorrect in WebAssign. So for example, Look what happens here if we just rounded the mean to 1 decimal place. We would come out with an answer of 2.61. Well, that's really close to 2.59. No, but we were better off just getting the accurate answer. So the important point here is don't do the standard deviations the long way by hand. Let the computer do the work for you. At this point, you should pause the video and do in-class exercise number 4 on page 5 of the orange book. Now, when you're doing this, there's a first little list of numbers, and you're going to find the mean, median, and not the IQR. That's why I have that one grayed out. And then in the second row here, there's another list of numbers, and pay attention to this question. How does this list compare to the list in part A? And then again, when you get to C, how does this list compare to the list in part A? And likewise for part D, because you'll need that information to fill out the chart on the bottom, which I think you'll see when you get to that part. So next, you can pause the video here and double check your work on this top half of in-class exercise 4. So let's go through the bottom half of the page together. So which of these 3 are measures of the center? That is the mean and the median. Which leaves the standard deviation is the measure of the spread. Which one is the balancing point of a histogram? That is the mean. Which of these are always positive? So all the examples we've done so far, all the numbers have been positive. All the numbers up on the top half are positive. But which ones are always positive? So, we could be dealing with temperatures up at the Arctic. We could get negative numbers there, a negative mean or a median. We could be dealing with what was a weight change if someone went on a diet, in which case those numbers could be negative. The average could be a loss in weight. But when we calculate a standard deviation, we take those deviations from the mean and then we square those. And so anytime we square something, the result is a positive number. So we add up positive numbers, and the end result always has to be positive. It's a form of a distance measure, and distance is also always positive, so that's another way to think about it. Now, which one of these are affected by outliers? Okay, of the mean and the median, we talked about this. The mean is affected by outliers, but the median is not affected by outliers. And we can see that in this little example up here. The difference between A and B is in B, this 50 is changed to a 75. You see that changes the mean, and it does not change the median. This number on the end could be 750, and the median would still be 45. Now, what about the standard deviation? Well, the standard deviation uses the mean. So if the mean is affected by outliers, then the standard deviation is also. In fact, it's even more affected. So we see that it changes from 3.42 to 11.59. So before we go on to the last 2 columns, let's look up here, and what's the difference between list A and list C? What did I do to list A to get list C. So hopefully you figured this out, that list C was A plus 10. And what did I do to list A to get list D? And what I did here is I took list A and I multiplied it by 2. So now let's look at how does A compare to C? Okay, well, the mean in C is 10 larger than A. The median is 10 larger. But the standard deviation did not change. So what's happening here is when we add a number, it's like we took that whole distribution and we just slid the whole thing down the number line. You know, the whole histogram, we just slid it down. So how spread out the observations are relative to each other does not change. So in the lower half, this column that says changes when same number is added to all observations, the mean and the median change, but the standard deviation does not. Now, what about D compared to A? Okay, well, the mean is twice what it was. The median is twice what it was. And the standard deviation is twice what it was. There's a little bit of rounding error on that one. But also note here how these changes are predictable. Okay, when you add the same number, that same number gets added to the mean and the median. When you multiply by a number, then everything, all the measures are multiplied by that number. So that's going to be key to answering a couple of the homework problems, or at least making them a lot quicker to answer, is to know what these predictable changes are. So now, just to finish up, I'm going back over to the blue book on page 29. And here's just a picture of what the histograms look like when we add or multiply by a number. So for example, if we start with this histogram, if we add 40, we just take this and we've slid it down. So it's the same shape, it's just in a different location. However, if we multiply by 2, what that does is it takes it and it stretches it out. So the spread and the center change. Or if we divide by, for example, 2, what that does is it shrinks it. So multiplying and dividing either stretch or shrink. And at the bottom, there's a question: if you have a list of numbers and you subtract the mean from each number on the list, what will the new mean be? So subtracting is, well, sliding it in the other direction. So if we slide it over by the amount of the mean, that means that it's going to be centered at 0. And we had a question on the last homework assignment where you actually had worked through those calculations. So now on page 29, I want to take a look at these two histograms. And can we tell, just by looking at the histogram, not having the exact numbers, can we tell which of the standard deviations is going to be larger? Okay, well, this one clearly has a larger range. And the range is also a measure of dispersion. Okay, but we need to think more carefully about what it is that the standard deviation measures. So if we look at this top example, okay, it's close to being symmetric, so the mean is, somewhere close to that. And this says like the bulk of the observations, the largest group is here, tightly bunched in around the mean. So these all have small deviations. Most of the observations have small deviations. But what if we look at this bottom example? Well, the mean is going to be like somewhere in between these two peaks. So there are almost no observations that have really small deviations, and the bulk of the observations have much larger deviations than in the top example. And this lower one is going to have a much larger standard deviation. So this has been a long video, a lot of information about the standard deviation, but like in conclusion, like what is the standard deviation? Well, the population standard deviation is the square root of the average of the squared deviations from the mean. Okay, but that's a long sentence, a lot of math words there. So can we just kind of summarize that, shorten it? So really, what is the standard deviation? Well, it's population standard deviation is the square root of the average of the squared deviations from the mean. That's what it is. We can't shorten it. That is the definition. It isn't anything more magical than that. Now, there is a situation where the standard deviation does have some more intrinsic meaning. And that's when we look at a bell-shaped curve, where we'll see that we'll call it a normal distribution. So the bell-shaped curve is symmetric around the mean. And the point where the curvature changes from concave down to concave, which is called an inflection point, this distance right here between the mean and the inflection point is the standard deviation. So it does have some magical properties, but only for this bell-shaped curve. And when we have this bell-shaped curve, we know that 68% of the observations are within one standard deviation of the mean. So a misunderstanding of the standard deviation is that is the definition, that the definition of standard deviation is the point where 68% of the observations are within the mean. But this is only true for the bell-shaped curve or the normal distribution, not for all distributions. It's not a general definition of standard deviations. Okay, and so what I said there on the previous slide is written out here in sentence form down here. So this is the end of the standard deviation video, and next you should do the standard deviation WebAssign.